DeepTake, prediction of driver takeover behavior using multimodal data. I'm Erfan Pakdamanian and I'm presenting this paper on behalf of my collaborators. DeepTake Overview. In Level 3 of automated driving, drivers are not strictly forbidden to engage in non-driving related tasks. Drivers are still expected to intervene and take over vehicle control when takeover request is issued by the system. However, if a driver is engaging in non-driving tasks, there will be a sudden increase in workload and stress. To cope with the safety challenge of takeover, we propose DeepTake to reliably predict takeover intention, time, and quality together. Since driving is full of uncertainties, and because every possibility should be programmed into the vehicle, accidents and unforeseen results will happen. Although the future will be autonomous, our quest to get there needs a transition period to better integrate human and machine expertise in safety-critical situations. Since the high-level goal for automated vehicles is to be reliable, safe, and trustworthy, we should move toward designing humanistic or human-centered systems to create more effective and safer human automation collaboration. As drivers are allowed to engage in non-driving activities, maintaining them vigilant to properly react in critical situations is crucial. So the question becomes how long it takes drivers to reclaim manual control and what factors determine a safe takeover. Previous studies have addressed this issue in two major areas. One, evaluate takeover performance with respect to takeover time, takeover quality, and some investigated predictive models for estimation of either takeover time or takeover quality. However, they obtained relatively low accuracy for on-road applications. So, we still need an enhanced system to not only estimate all aspects of takeovers, but also be more robust for real-world applications. Secondly, some studies investigated different modalities. In most of these studies, takeover requests were presented unfailingly. Therefore, such takeover requests bear a little resemblance to real automated driving. DeepTake, on the other hand, is the first framework which integrates a deep neural network model to predict driver takeover intention, takeover time, and quality. We envision that DeepTake can be integrated into future automated vehicles, such that the automated systems can make optimal decisions based on the outcome of DeepTake. For example, if the predicted takeover time is high and takeover quality is low, the automated system can warn the driver to engage less with non-driving tasks. In addition, we utilize three types of alarms: true alarm, false alarm, and no alarm, because in the pre-crash world, automated vehicles should be expected to fail to always provide correct takeover requests. So the scenarios were constructed conservatively to include flawed takeover requests. For the research presented in this paper, we conducted experiment with 20 subjects. To capture their readiness, cognitive, and physiological states before issuing takeover requests, we used biometric signals. Each participant drove through 3 trials followed by a 5-minute break between each. Within each trial, we also designed various events. Participants were also asked to engage with 4 non-driving activities. In each trial, 15 takeover requests occurred, with 6 true alarms, 6 false alarms, and 3 no alarms. 45 takeover requests in total. All the captured data were then chunked to 10 seconds before the takeover request in order to predict what will happen after the takeover request initiation. This chunk of data was then pre-processed, labeled, and meaningful features extracted from. Finally, these chunks of data were fed into the neural network with 3 hidden layers. To extensively evaluate the performance of DeepTake, we use multiple metrics and compare the result with 6 off-the-shelf models. First, we compare the algorithms in correctly classifying takeover behavior. The result shows that DeepTake achieves significantly higher accuracy as opposed to the other models. Second, ROC curve was applied in order to better evaluate each of the classifiers. DeepTake shows outperformance on correctly classifying all aspects of takeover behavior. Finally, in order to draw better insight in performance of DeepTake, we use confusion matrix to measure the rate of misclassification for each class of takeover behavior. Overall, marginal misclassification were found in takeover intention and time, but more incorrect classification in takeover quality. To sum up, with the presented novel framework, DeepTake, we extend previous literature by providing new insights on predicting takeover intention, time, quality together. More specifically, we provided a reliable framework which can be applied in real-world applications. We also tested flawed takeover requests on takeover performance. Thank you for tuning in.